Now, last time there were some questions which I'll answer. So what I'll do is I'll share a file.
Are there? So we must times 6 are 2 times 11. Are terms of gravity you are
Yes, sir.
All right.
okay.
So last time we were discussing Bernoulli's equation.
Okay.
And
That you have to put.
you may recall that we had defined a function that we called capital B,
Okay.
B for
So I
Bernoulli,
will write here
which is the sum of these three quantities: pressure, then minus rho G dot R plus half rho V dot V. Now for us, rho is constant because we're dealing with flow of water. The pressure itself can vary from point to point. G dot R, of course, will vary from point to point, and the velocity can also vary from point to point. Now, if the flow is unsteady, then the velocity will vary with time also at a given point. Similarly, the pressure may also vary with time at a given point. But if you say the flow is steady, then the sum of these three quantities is a constant, provided these conditions are satisfied. The flow is steady, the flow is inviscid, the density is constant, and the gravitational force field, the acceleration due to gravity is a constant. But the numerical value of this function B may vary from one streamline to the next. So if I say that 1 and 2 are 2 points which are on the same streamline, then when these above conditions are satisfied, B2, the value of B at point 2, will be equal to the value of minus rho G dot R2 plus half rho times V2 dot V2, which is the sum of pressure, the potential energy per unit mass, per unit volume, and the kinetic energy per unit volume. These three quantities at the point 2 will be equal to the same quantities at the point 1. So on the right hand side, you have P1, the pressure at point 1. This is the static pressure or absolute pressure. Then you have minus rho G dot R1. R is the position vector at point 1, and plus half rho V1 dot V1. Okay. Now another way to write it is move all the terms to one side of the equation and write it as sum of several terms equal to 0. So here I grouped the terms so that you have within the first parenthesis the change in the pressure P2 minus P1. Then you have the change in the potential energy per unit volume minus rho G dot this difference R2 minus R1, which you can think of as the displacement vector between 1 and 2. And then you have half rho V2 dot V2 minus V1 dot V1. So this is the magnitude of V2 whole squared minus the magnitude of V1 whole squared. So if you want to write in words, you say that when you move from point 1 to point 2, the increase in pressure plus the increase in the potential energy per unit volume, of course this is gravitational potential energy, plus the increase in the kinetic energy per unit volume of the fluid, this must add up to 0 when these four conditions are satisfied. The flow is steady, viscous forces are negligible, the density is constant, and the gravitational acceleration is constant. Now there was a query last time regarding whether you can call this a kind of energy. Okay. I don't remember who called, who asked this question. Now I have a request to you. In future, if you ask a question, please introduce yourself and then ask the question. See, in a normal classroom, I get to see you. Here, I'm not able to interact with you on a personal basis. So I think it's a good idea if you ask a question, first, please introduce yourself. Now, I don't know, the person who asked this question, is he here today?
Hello. Hello.
Hello?
Yes, sir. I had asked the question, Vishnu.
Okay, good.
Yes.
So let me answer the question. Okay. If you look at Euler's equations of motion, and this is of course valid, of course I've dropped the unsteady term, so I'm looking only at steady flow now of a constant density inviscid fluid in a constant gravitational force field. You have the convective acceleration term on the left hand side and the two forces on the right hand side. So the way this is written, this is mass times acceleration per unit volume. Of course, this is only the convective acceleration. The temporal acceleration is 0. The first term on the right hand side is the body force per unit volume, because rho is m upon v and mg is the body force. And minus grad p is the net pressure force per unit volume at that point. Now, of course, you may ask, what is the meaning of force per unit volume? Well, I've already answered that question in a previous class. To give a physical interpretation, you multiply each side of the equation by dV, the volume of a particle. Okay, and then you can get, on the right hand side, you will get the body force on the particle, and the net pressure force on a particle of volume dV is minus grad p dV. Now, if g is a constant acceleration vector, then we have seen that you can write it as grad of g dot r. And this term also, if density is a constant, I can divide by density and write it as, and multiply by density, write it as minus rho grad of p upon rho. So what I've done is I've introduced two functions. I'm calling E with the superscript GRAV for gravity. So this is the gravitational potential energy per unit mass. Okay, so this is minus g dot r, this quantity. Okay, so the minus sign is there so that it becomes a potential energy. You know that gravitational potential energy is the negative of the work done against gravity. So that's why the minus sign has been introduced. So I have introduced one minus here and written this as another minus here. So this is a function only of position. It is gxx plus gyy plus gzz, this sum, and you have a minus sign outside. And the other quantity I am writing as E with the superscript PRESS for is the kind of potential energy associated with the pressure. So this is the pressure, which is a function of position divided by the density. Now, in general, of course, density can vary with position as well as time. But we are dealing with the case where the flow is a constant density flow. Okay, like so that is a good approximation when the fluid is a liquid, such as water. Now the pressure field can also vary with time as well as position. In that case, it will not be a potential energy. Okay, so whenever you can write the force as grad of a scalar potential, which depends only on the position, okay, then you can call it an energy. And P upon rho I can also write as P times the specific volume V. And you may recall from your thermodynamics course that P multiplied by V is referred to as flow work, or to be more precise, the flow work per unit mass. So if you have a small particle of mass dm, when it moves, it pushes the fluid ahead of it. Okay, and in the process it does a work which is PV multiplied by dm. But when these two conditions are satisfied, that the density is a constant and the pressure field is steady, that is independent of time, then we are able to write this force as the density multiplied by grad of a scalar potential which depends only on x, y, z. In that case, you can interpret it as a sort of potential energy associated with the pressure field. But a word of caution, suppose the pressure field is unsteady, okay, then this will no longer cannot be interpreted as a energy. Or if the density varies from point to point, then also you cannot do that. Okay. So talking about pressure, energy might be misleading, but in this particular case, the work done against this pressure force gets stored in the form of energy and it can be recovered. So that you have the change in pressure plus the change in potential energy plus the change in kinetic energy is 0. So have I answered that question?
So like I had thought about this, like we have said that the work done by the pressure gets stored in the fluid, right?
Yeah, it gets stored in the fluid as energy when it is a steady pressure field and the density is constant.
But sir, like in general, like such a storage of energy would be expected with compressible flows, right? Like kind of like stress energy or something like that.
Well, in the case of a gas, if it expands, you can get and the pressure reduces, you'll get some work done. Okay, but
Yes,
the
sir.
work done may not be exactly P2 minus P1 by rho, per unit mass. Okay, so this is as I said, this is potential energy per unit volume. If you divide the whole equation by rho, then it becomes potential energy per unit mass and kinetic energy per unit mass. Then you will have P2 minus P1 by rho. Okay.
Yeah.
So if we allow the pressure to fall, in the case of a gas, you'll definitely get some work out of the, but that workout will not be P1 minus P2 by rho, as in the case of a liquid. So quantitatively, it is not correct to say that this is a pressure. This is a kind of potential energy.
Yes, sir.
Okay. All right. Now I didn't get time, but then next time, if you still have some doubts, I'll consider motion of a particle from mechanics point of view and explain it to you again. For the
I'll
time,
also look into it. Like what I'm thinking now is like considering some compressible flows and like tending it to this incompressible limit might yield this thing. That is what I'm thinking.
okay, in the case of a compressible flow, suppose I take this vector equation, okay, and take the scalar product of each side with displacement vector dr, let us say, okay,
Yes.
which may represent the displacement of a particle, okay. Then rho g dot dr, if I multiply by dv, rho dv into g dot dr will be the work done by gravity, okay.
Yes.
Similarly here, if I multiply this by dv and take the dot product with dr, it will be the work done by the pressure field. Okay, pressure
That
force.
is the surrounding fluid on the fluid particle.
Right.
Yeah.
But pressure, net pressure force exerted by the surrounding fluid. Okay.
Yes.
Now dr dot dp, dot p, you can write as dp. Okay. Then it becomes dp. So if you want it per unit mass, then you get a term which is dp upon rho. Okay.
Yes.
So here if you write integral of dp upon rho, okay, then you have to replace p upon rho by integral of dp by rho. Okay. But then integral of dp by rho will become a path function unless you have a special case where rho depends only on pressure. And that kind of a flow is called barotropic flow.
Okay,
An
so this will have like this will correspond to something like magnetic field lines or like magnetic field energy for that matter.
No, if you have a magnetic field, then you have a different kind of potential energy.
Okay, modified potential energy. So can't we have that kind of potential energy here?
No, if it's compressible, then you will have integral of dp upon rho, perhaps. But if that is a path function, then it's not an energy. Okay. If the work done is a path function, it depends on the path, then it's not an energy. If the work
but the same
done,
is true in case of magnetic fields also, right?
the work done has to be a point function. If you can, only then it will be stored as energy.
Yeah, but probably some other formulation would be there. Because like the same would be applicable to magnetic fields also, right? Because they are closed loops. So even in closed loops, magnetic field, like this appears to me to be analogous to magnetic fields.
Now, if you look at the magnetic field, there will be a Lorentz force which will be J cross B. J is the current density and B is the magnetic field density. Okay, that may not be a conservative force field. Okay, so the force field has to be what you call conservative, that is expressible in the form of gradient of a scalar.
Yeah, only then we can define potential energies.
Right, only then you can call it a potential. Okay. Otherwise,
So,
it's not a potential.
The energy
There may be
formalism
work
itself
done,
is
but
not
it will not be
applicable in
stored as
such cases.
energy.
So, sir, the formalism of like energy approach is not applicable to such cases.
No, no.
Yeah, okay. Yes, sir.
You cannot call it pressure energy. Okay.
Mm.
So it is misleading to talk about pressure energy. And anyway, this potential energy is not P, it is P upon rho. Okay.
Yes, sir. So in such scenarios, we cannot even talk about energy conservation.
No, no.
Yeah.
But in the special case that we are considering, where the density is constant, and if the flow field is steady, then
turns out that the
then the flow
those
work will
terms
be
contribute to a point function rather than a path function.
Yeah. See, work done is always not work is not always converted to energy. Some of it may be dissipated.
Yes,
See, work done against friction, that is considered a loss.
Yeah, then first law of thermodynamics will come into picture.
Loss of what? Loss of available energy. Okay.
So something like that happens in refrigeration systems also, right?
Exactly. Right. So the internal energy will increase and the entropy of the universe will increase. It's not a reversible work mode.
Exactly.
You know what is a reversible work mode?
Reversible work mode. Like quasi-static processes are reversible in thermodynamics. Right?
See, a work mode is reversible if and only if it can have both sides, plus or minus. That is, you can do work on the particle or the particle can do work. Okay. But if you look at work done against friction, it always will have the same sign, because suppose the particle is moving in the positive x direction, then the force will be in the negative x direction due to friction. So F dot dr will be negative. Okay. But suppose the particle is moving in the negative, in the opposite direction, the direction of the force will change.
Yeah, so the dot product is still the same. Yeah, negative.
So dot product is always negative.
Yes, sir.
So that is an irreversible mode of work. Okay. But if you look at work done against gravity, gravity is always vertically downwards. When you move a particle upwards, you are doing the work. Okay. And that gets stored as potential energy. If you allow the particle to move downwards by the same vertical distance, it will do work, because the direction of the force is unchanged. Okay.
Yes, sir. Yes, sir.
So that way, PdV work is also reversible work, because pressure is always positive and dV can be plus or minus. So if it expands, the gas is doing work. If you compress it, you have to do work. Okay. But that is not stored as energy. Okay. For it to be an energy, it must be of the form gradient of a scalar potential, which depends only on the position.
So despite of it being in a reversible mode, still like in some scenarios, energy might not be valued.
If you look at a simple example, let us say you have an ideal gas in a cylinder with a piston. All right.
Yes,
suppose the gas expands, so volume changes, and it's a quasi-static process. Then the work done will be integral of PdV. Now that will depend on how P varies with V. It's a path function. If you have an isothermal process, you'll have one path. If it's an isotropic process, so if it's isothermal, then PV will be RT. Okay, or PV will be constant, let us say. If it's reversible adiabatic or isentropic, then PV to the power gamma will be constant. Then the work done will be different. Okay.
But
So
sir, in
although
that case, the
PDB work
final
is
state
reversible
arrived at is
work,
also different, right?
uh,
In case of different processes.
yes, PDB work is reversible because it can be plus or minus, but the work depends on the path. Then it's not an energy, not a potential energy.
Yeah, so like I was thinking about the same thing. There's like this kind of thing in magnetic fields also. We can't define it as potential energies, right? But
No,
then like we introduce field energies and something happens, I think.
heat is not potential energy. Heat is just energy in transit.
Yeah, heat is a completely different form of energy, right?
Right, right.
But I understood that like we can't call it potential energy because it's path dependent, of course.
Right, right.
But in the same case of magnetic fields, like
Magnetic
there
field
are some,
also,
yes sir,
yeah.
there are some other formalisms as far as I've heard. Like they introduce field energies and they do something so that conservation of energy still holds.
If you look at say flow of a plasma, or it could be a liquid also, which is electrically conducting. Okay, and suppose you have an electric current flowing through it. Then on the right hand side of this equation, you will have an additional term which will be J cross B. J is the current density, and B is the magnetic field density. Okay,
Yes sir.
so J cross B will not be a conservative force field. Okay,
Yes sir.
but if you have a electrically charged fluid, okay, the
Yes.
electrostatic force might be conservative. Depends on the situation.
Yeah, like if it's generated by a very magnetic field, then to no. Yes sir.
Okay. Now another question that was asked is regarding the variation of this quantity, which I call V. Okay. I said that it is constant along a streamline, but the numerical value can vary from one streamline to the next. Okay. So let us answer that question. Okay. So I've considered now the Navier-Stokes system. So let us look at the viscous effect also. Suppose the density is constant, and we'll assume viscosity is also constant. Then the local form of conservation of mass is divergence of V equal to 0. That is what you may call the continuity equation. And if you look at the momentum balance for a Newtonian fluid, okay, you will have this additional term, mu into Laplacian of the velocity. Now, for an ideal fluid, mu is 0, so this term is not there. Okay, so I'm considering viscous effects also. Now, in your second semester, you've studied vector calculus, so you might have been asked to derive this following identities as an exercise, and you might have also seen them in your second year course on fluid mechanics. V dot grad V you can write as minus V cross curl V plus grad of V dot V by 2. Okay, so this was first shown by Lagrange or used by Lagrange in the context of fluid mechanics, and it's called Lagrange's acceleration formula. And this is another useful identity, that Laplacian of V is grad of divergence of V minus curl V. Okay, so using this, if you recognize that curl of V is what you call the vorticity, I'll use the symbol omega here. Okay, so instead of V dot grad V, I can substitute these two quantities. Okay, so left hand side I will write as the temporal acceleration, and in place of the convective acceleration V dot grad V, I'll write these two terms. One is this conservative form, grad of V dot V by 2, and the other is minus V cross the vorticity. Now right hand side, if G is constant, we know that we can write it as grad of G dot R, and for the timing I'm leaving grad P as it is. This term, now divergence of V is 0 at each and every point. Okay, So grad, if I take del del x of either side, it will be 0. Del del y of other side will be 0. So grad of divergence of v is 0. So Laplacian of v then I can write as minus curl of omega. Okay. So you have a disguised form of the Navier-Stokes equations. Rho times del v del t minus v cross omega. Okay. Now what I have done is, since grad is a linear operator and we are assuming density to be constant, I can move this rho inside. Okay. And similarly, this rho I can move inside this term. And I can club this term of last term on the left hand side with the first term on the right hand side as well as the second term on the right hand side, and write it as minus grad of this whole quantity, which is p minus, I missed a rho here, sorry, rho g dot r plus half rho v dot v. Okay, so this you will recognize as what we were calling the Bernoulli function v. So if I move this to the left hand side of this equation, and if I move the other terms to the right hand side, we will have grad of v equal to minus rho del del t of the vector v plus rho times v cross the vorticity minus mu times curl of the vorticity. Okay. So this whole equation over here is a form of the Navier-Stokes equation. Okay. For the special case where the density and viscosity are constant. Okay. Now this tells you how, what are the quantities or physical mechanisms which cause a change in V. Okay. One is unsteadiness, one is the vorticity, and the other is again the viscous effect related to vorticity. Okay. So grad V will be the zero vector if the three terms on the right hand side are 0. Okay. When that happens, then this grad V equal to this is the zero vector. So this is a vector equation which is equivalent to three scalar equations. Del v del x equal to 0, del v del y equal to 0, and del v del z equal to 0. So this will occur if the flow is irrotational. That is omega vector, which is curl of the velocity vector, is 0. And del v del t is a zero vector. This will happen if the flow is steady. And the other two conditions are coming because this equation, as I said, is for the case when density is constant and the gravitational acceleration is constant. Now, if the flow is steady, then del del t of v will also be 0 at a given point. So if v doesn't vary with x, y, z and v doesn't vary with time, then v is a constant. So the function v, which could in general depend on position as well as time, will be a constant. This is a global constant valid for each and every point in the flow field if these following conditions are satisfied. The flow is irrotational, the flow is steady, the density is constant, and the gravitational acceleration is constant. Okay. Under these conditions, you can apply Bernoulli's equation between any 2 points in the flow field. They need not be on the same streamline. But if you consider, say, inviscid flow, mu is 0. If it's steady, del v del t is also 0. But you could have steady inviscid rotational flow where this vector omega, which is curl of v, is non-zero. Okay. In that case, grad of v will not be equal to 0. Zero vector. So v will vary with position, but if you move along a given streamline, then the change of v will be 0 because if you along a streamline, this quantity v cross v is perpendicular to v. So if I take the scalar product of this equation with v, left hand side will be v dot grad v, and right hand side, suppose it's steady, this term is 0, suppose it's inviscid, the last term is 0, and this term is non-zero, but v dot v cross omega will be 0 because v cross omega is a vector perpendicular to v. So if you take the scalar product with v, it will be 0. So v does not vary if you move along a streamline, but if you move in a direction normal to the streamlines, then v can vary even if the flow is steady, density is constant, acceleration due to gravity is constant, but this quantity, the vorticity, is non-zero. Okay, so have I answered this question? Now you can ask why I did not write the viscosity here, because even if it's a viscous flow, if it's irrotational, then the last term will be 0. So you might ask, can you have viscous irrotational flows? And the answer is yes, but only in very special cases. There are some cases of viscous irrotational flows, but in general, viscous flows will be rotational. So the omega will be non-zero. Hence, this Bernoulli constant will vary from point to point, and you cannot apply Bernoulli's equation between any 2 points. It must be 2 points on the same streamline. Okay, now any other questions regarding this part? So I'll stop sharing this document and open another document. Okay, so let us come back to the discussion which we had yesterday. This has some relevance to the Pelton turbines, but to fix the plane is moving to the left with a velocity v0. Okay. Now, to analyze the flow, you can either use a fixed coordinate system, which I've shown on the left over here, and you can have an observer, a person whom I'm calling observer A, and let us say he measures the velocity at a point P, which is fixed relative to the ground. Okay. Now, when this plane, which is on the right, is far away, the velocity here will be 0. So when the plane is moving, it will push the fluid around in front of it, okay, and set it into motion. So as the plane nears this point P, if you measure the velocity at point P, you will see that you will begin to see a non-zero value. And after some time, when the plane has gone far away to the left, okay, due to the viscous forces, the velocity will damp out, and again it will become 0. But if you are measuring the velocity here, it is initially 0 and finally 0, but in between there is a non-zero values. So the flow, you will say, is unsteady as seen by observer A at a point when the measurement point is fixed relative to the ground frame. Now, if you consider another frame of reference which is translating, and let us say you have a person sitting on this frame inside the plane, whom I am calling observer B. Excuse me. Let us say you have point Q, which is fixed, whose coordinates are fixed relative to this frame, moving frame. And observer V is measuring the velocity at this point. Okay. Now what observer V will see? Well, he'll not feel the motion of the plane because he's inside. He'll see the air moving in the opposite direction with the velocity of the plane. So if I go back and say observer V sees the plane moving from right to left with the velocity magnitude of V naught. V naught is the speed and the direction is in the negative x direction. Okay. Then observer B sitting inside the plane will see the fluid moving in the opposite direction, in the positive x direction, which is the same as the positive x prime direction. Now he will see the flow to be steady over here. So the same flow is steady in the translating frame of reference, but unsteady in the ground frame. Now I have introduced this term which I call relative streamline. You can think of it as a curve in space that is everywhere tangent to the relative velocity vector. Okay. So if I use in this translating frame the velocities as measured by observer B, okay, then the equation of the streamline will be similar to what we have seen before. Only thing is I'll use this prime coordinates x prime, y prime, z prime, which are coordinates measured in the by the observer B in the translating frame. And I'll use the relative velocities wx, wy, wz, or vx prime, vy prime, vz prime. All right, now let us consider this Pelton turbine, and this is the bucket. We have a frame here. This is a two-dimensional view. So I've shown just OXY and observer A fixed to the nozzle, which is stationary. So this is the ground frame. And observer B is moving with the vane or bucket, which is translating with velocity capital U, which is a constant velocity. Now, the fluid, the liquid here will impinge on the bucket, and due to the curvature of the bucket, it will be forced to turn, it will be deflected, and it will move out backwards. But because this solid surface which is hatched here is impermeable, the full fluid cannot go through the solid. So the normal component of the relative velocity will be 0, and the relative velocity vectors will be tangent to the surface. So you can see that this surface, the wetted surface of the bucket or vane adjacent to the liquid jet, is a streamline as seen by observer B. So I am calling it a relative stream surface. And this interface between the liquid jet and air, you have air above, you have air below. That is also another streamline because there is no flow normal to it. It is another relative streamline. Now, observer A will see the streamlines moving or translating. So if the streamline pattern is moving, then the flow as seen by observer A is unsteady. But observer B will always see a streamline pattern which is stationary. So the flow as seen by observer B will be steady. Now why are we doing all this? Because when you analyze the flow, you will have an unsteady term, and quite often in a second year course on fluid mechanics, you have made an assumption that the flow is steady, so that term is either identically 0 or it is small compared to other terms in the equation, so that it can be neglected. So the point is that we have emphasized it so many that Bernoulli's equation you can apply only when the flow is steady. So now, if observer A measures the velocities, suppose the velocity magnitude is v, then you cannot say p plus half rho v square plus rho gy is constant along a streamline because the flow is unsteady. So here minus g dot r will become, if I say g is in the negative y, the potential energy term will be rho gy. So therefore, if I look at point A and point B, okay, I cannot say that the pressure at point A, which is of course equal to the pressure at point B because of atmospheric pressure, okay, and the change in the is usually negligible. This is an enlarged view. So the question is the velocity at point A equal to the velocity at point B? They cannot be the same because the sum of pressure, kinetic energy, and potential energy is not conserved because the flow is unsteady. So the velocity at point B will be different from the velocity at point A, the absolute velocity. Okay. And if you're thinking of extracting work from the fluid, what is the energy conversion? You're converting the kinetic energy of the fluid to the mechanical energy or kinetic energy of the moving bucket. Okay. So that is possible only if the velocity at B is less than the velocity at A. Okay. So the absolute velocity at point B you would want to be less than the absolute velocity at point A. Now, can you think of a situation where the velocity at point A and the velocity at point B will be the same? The absolute velocity. Is the question clear? Let us say you have a parameter here, which is the speed of the vane, u. Then
U is 0.
Okay, when u is 0, the bucket is not moving. All right. So observer B and observer A, they'll see the same streamline pattern. In that case, this will not be a relative streamline, but an absolute streamline. Okay. Then you can apply Bernoulli's equation between A and B, these being points on the same streamline. Okay. So when the vane is not moving, the velocity at B and the velocity of A will be the same, assuming that viscous effects are negligible. Very good. So now I think you are beginning to understand things. Okay. But even if the flow is inviscid, if the vane starts to move here, then the velocity at B may not be the same as velocity at A. Okay. And if the velocity at B is less than the velocity of A, that is good news for you as a mechanical engineer, because then you can see the kinetic energy of the liquid jet being converted to work. Okay. So there will be a resisting force on this vane so that the velocity is constant, otherwise it will accelerate. Okay. So if there is a resisting force and if it moves, then you have work done. Okay. But simultaneously, the kinetic energy must decrease, kinetic energy of the liquid jet. Okay. So this is the simple physics, but to make quantitative predictions, then you have to look at the equations, the mathematics. Okay. So I've written here the Euler system of equations for an ideal fluid, first in a stationary frame of reference. Now, once again, ideal fluid means viscosity 0 and density constant. So if density is constant, the continuity equation is divergence of V equal to 0, and the momentum equation, if density is constant and G is a constant vector, I can club the body force term with the pressure term by defining a modified pressure which I've called P star, the piezometric pressure. Then I have on the right hand side one term, one group of terms, and left hand side one group of terms. So left hand side represents the inertia force, and the right hand side negative of the inertia force. Right hand side is the pressure force. All right. Now, why have I written this first equation? Can anyone tell me? If I look at just this equation, the momentum equation, can I find the solution of the flow field?
So two variables are required: vector, velocity vector, and pressure.
Okay, let me write it in the Cartesian form. So there are three equations. This second equation here is a vector equation. It has three components. So there are three scalar equations: the x momentum, y momentum, and z momentum equation. Okay. Now, what are the unknowns in this equation? Vx, Vy, Vz, and P star. So there are four unknowns. And if you just look at momentum balance, there are three equations. So you cannot have a mathematical model where there are four unknowns and three equations. That's not solvable. You must have a fourth equation. And in this case, it is the quantitative equation. Okay. So that is why I'm calling it system of equations. Okay, Euler's equation is just this second equation, second vector equation here. First one is a scalar equation. But if you want a system of equations that you can solve in principle, then you must have number of equations equal to number of unknowns. So without looking at the quantitative equation, you cannot find the solution of the momentum equation in general. So that is why I have called it system of equation, Euler's system of equation. And I have included the quantitative equation in addition to the momentum equation. Now this form I've written it as V dot grad Vx and V dot grad Vy and V dot grad Vz to show you the similarity between the three. Of course, V dot grad itself has three terms. So this is what is called the non-conservative form. Okay. Now, there is also another form which you may call the conservative form. So you can show that if divergence of V is 0, this first equation is valid, then V dot grad Vx you can write as divergence of Vx V. In general, of course, you have to subtract off a term which is minus Vx divergence of V, but that term is 0. So here you have inside the divergence operator. So here it was V dot grad. This is called non-conservative form. And this is called conservative form, which is divergence of Vxv. And if you look at the analogous term in the y and z momentum equation, it just replace Vx by Vy and Vz. And this V remains as it is. Now, if you take a course on CFD, computational fluid dynamics, you see that finding the numerical approximation of this equation, which is mathematically equivalent to this equation. Okay, there are some advantages in discretizing this form of the equation. So there you call it conservative form. Okay, so that's just a terminology. Mathematically, the two equations are equivalent. But then if I ask you to look at this equation and integrate it over a volume, okay, then integrating this equation is easy because integral of divergence of a vector field you can easily convert to a surface integral. Whereas if you look at this form, it is not so simple. So that's why I've introduced this form. Okay, now we want to look at Euler's equations in a translating reference frame. Okay, so here for the timing, I'm not giving you the derivation, just showing you the form. Okay, so if you recall, I've introduced the operators before, but let me do it again. Okay, so you have the fixed frame here with coordinates x, y, z, and a moving translating frame with coordinates x prime, y prime, z prime, which are related by this equation. X prime is x minus ut minus some constant, and y prime and z prime are the same, and t prime is t. Okay, so the position vectors you can either write as x ex plus y ey plus z ex, or x prime e prime x plus y prime ey prime plus z prime ez prime, and the unit vectors are the same because they are parallel vectors in this case. And similarly, I can write the velocity vectors this way: absolute velocity as measured by the stationary frame in the stationary frame, and the relative velocities as measured by an observer in the moving frame. Okay, and we can have two grad operators, one which has del L x, del L y, del L z, and ex, ey, ez, or del L x prime, del L y prime, del L z prime, and the vectors, unit vectors e prime x, e prime y, e prime z. We have seen this before. And similarly, you can have a divergence operator and a material derivative. Okay, where instead of del L t, you have del L t prime, and you have the relative velocities and the gradients, partial derivatives with respect to the moving coordinates. Okay. All right. So now you can show that you can have a form of Euler's equation where you have the relative velocity and this divergence operator del dot, del prime dot equal to 0. And you have this material derivative d t prime, and this is grad prime. Okay. So in Cartesian form, you will have del L x prime of wx plus del L y prime of wy plus del L z prime of wz equal to 0. And here you will have w dot grad prime of this. Okay. So if we compare these equations, again you will have 4 unknowns and 4 equations. The form of these equations is similar to the form of these equations. Only difference is now that instead of t, you have t prime. Instead of x, you have x prime. Instead of y, you have y prime. And instead of z, you have z prime. And in place of vx, vy, vz, you will have wx, wy, and wz. So this is Euler's system in a translating reference frame. And similarly, if you want the conservative form, you can write it as I've shown over here. So the conclusion is that if you do the derivation, you will see the y they're the same. But you can make a statement that Euler's equations of motion are invariant under a Galilean transformation. Invariant means the form is the same. And therefore, if the flow is steady in the translating reference frame, then you can integrate it, the Euler's equation of motion, along a relative streamline, just as we did for the case of Euler's equation in a stationary reference frame. And then you will get what you may call Euler's, the Bernoulli equation in a translating frame of reference. Okay, now in this format, I'm just giving you the result for the time being. So we are going very fast. Okay, I think it is a good idea to take a short break before we move further. So if you have any queries, I can answer now. Otherwise, we'll take about a 10-minute break. And then we'll see why we are doing all this.
Sir, why are the Euler equations invariant under Galilean transformation? There's a del t, right?
Could you say that again, please?
Sir, you wrote that Euler equations are invariant under Galilean transformation.
Why they are invariant?
Yeah, because there's a del t, right? Del t will change.
Okay. Okay, so this is a forward transformation. You're transforming x, y, z, t to x prime, y prime, z prime, t prime.
Yes, sir.
And
Yes, sir.
x prime is x minus ut. This you have seen.
Yes, sir. Yes, sir.
Now, here I have included the Jacobian of the transformation. That is, you can show easily show it's one. Well, suppose you have a flow quantity, which I'm calling phi. It could be Vx, Vy, Vz, or P. So there are two possible descriptions. One is you can view it as a function of x, y, z, t, or the same quantity I can view as another function f2 of x prime, y prime, z prime, and t prime.
Yes, sir. Yes.
And the two functions are related. So
Yeah.
that okay. Now, what is the relation between the spatial derivatives? You have to use the chain rule.
Yes, sir. Yes, sir. Yes, sir. Same. But time
So
derivatives
if you
will
use
be
the chain
different.
rule, you can show that del del x and del del x prime are the same.
Yes, sir. Yes, sir.
And del del y and del del y prime are the same. Okay.
Yes.
And if I go back to this figure,
Temporal derivatives are different. Understood. Yes, sir.
the unit vectors are parallel. Unit vector ex prime is in the direction of O prime x prime. And unit vector ex is in the direction of Ox. They are parallel vectors.
Yes, sir. Yes, sir. So,
okay.
Their derivatives are also like zero, basically. Yeah.
So, the unit vectors, the prime quantities, are the same as the original quantities.
Yes, sir. Yes, sir.
So, therefore, this grad operator, Ex prime is the same as Ex, and del del x prime is the same as del del x. And Ey prime is the same as Ey, and del del y prime is the same as del del y. And Ez prime is the same as Ez, and del del z prime is the same as del del z.
Yes,
so
sir.
these
Yes, sir.
operators are identical.
Yes, sir. Yes, sir.
And similarly, if you look at the grad prime divergence, it is del del x prime of
same
Bx
thing. Same thing. Yeah, yeah. Okay. Yes, sir.
So the operators are the same. Okay.
But sir, in Euler's equation, there is a material derivative. Yeah, yeah, exactly.
Material derivative is the same, but the Eulerian derivative is not the same. So if you use the chain rule, then you will have del del t is del del t prime minus u del del x prime.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
But then if I combine this term with this term, okay. So if I write del del t, it is del del t prime minus u del del x prime. Okay. So Vx minus u will be Vx prime.
Okay. Vx minus u will be Vx prime.
Okay, so if I add del del t plus Vx del del x prime, this sum of the first two will be equal to the sum of these two.
Okay. Yes, sir. Yes, sir.
Okay. So I'll leave it as an exercise, but when I frame the question, it will become obvious. Okay.
Yes, sir.
So
Yes,
del del
sir.
t is not the same as del del t prime, and Vx del del x is not the same as Vx prime del del x prime.
Yeah, but the sum is.
Okay.
Yes, sir. Yes, sir.
So this is a kind of total derivative. Total derivative is the same in both the frames. Because if you have a scalar quantity, which is just a function of time, the derivative must be the same. Okay. But the partial derivatives, the meanings are different because think of it this way. As an engineer, you're measuring quantities at two different points. In the first case, del del t is the time rate of change at a measurement point which is fixed in the ground frame. And del del t prime is the time rate of change at a measurement point which is moving, but fixed in the translating frame. So physical meaning of these two are
Yes, sir.
different.
Yes, absolutely.
Okay.
Yeah.
But the material derivative is invariant. Okay.
Yes, sir. Yes, sir. Understood. Yeah.
Okay.
Yes, sir.
So this is the reason why.
Euler's equation remains invariant under Galilean transformation. Yes, sir.
Right. So if you look at the sum del phi del t prime plus wx del phi del prime del x prime, this sum of these two terms will be the same as the sum of these two terms del t of phi plus vx is. Okay.
Yes, sir. Yes, sir. Yeah.
So if I look at Euler's equations of motion in the moving frame, all I have to do is use the velocity vector w and say these are the operators in the moving frame.
Hmm. Yes.
So now we can guess the form of Bernoulli's equation. Suppose I define a relative Bernoulli function B with a superscript REL, which is P minus rho G dot R prime plus half rho. Instead of V dot V, I have W dot W, the relative velocity. Okay. Then the value of this relative Bernoulli function will be the same at all points along a relative streamline. If the flow is inviscid, the density is constant and the gravity is constant. And in addition, the flow is steady in the translating frame. Okay. So if the flow is steady in the translating frame, then you can apply Bernoulli's equation along any 2 points on a relative streamline, provided you use the relative velocity here, magnitude of the relative velocity squared. Okay, so if I go back to this figure and consider a point A and a point B on this streamline, relative streamline along the free surface of the jet, or the interface between the liquid jet and the air. Okay, then you can say that PB plus rho G YB prime plus half rho WB prime squared equal to the same quantities here at point A. Okay, now I think it's a good idea now to take a short break. Okay, and I'll come back. So let us take a 10-minute break and then we'll discuss this again. So we'll see how to apply this and what is the relevance of all this to this course. Okay, so we'll meet after another 10-15 minutes. All right. Now let us go back and look at this figure of the moving vane of a Pelton turbine. Okay. So this is the nozzle, and water jet comes out of the nozzle and impinges on this vane, which is curved. The vane is moving with constant velocity to the right. And because this hatch surface, the solid surface, is impermeable, the fluid cannot go through. It will be forced to turn. It will be deflected backwards. So if it's an inviscid fluid, then the magnitude of the direction of the relative velocity at each and every point on the surface will be tangent to the surface. So we know the direction of the velocities. But what about the magnitudes? Well, we'll use Bernoulli's equation to find the magnitudes. Okay. So first consider 2 points A and B on this blue relative streamline at the free surface of this jet. So since the pressure at small a, this point, and this point small b will be the same as atmospheric pressure. So we'll apply Bernoulli's equation in the translating frame because the flow is steady in this translating frame. Between points A and B on the what you're calling a relative streamline at the interface between the liquid jet and air. Then you have the sum of these three quantities, pressure. Now the potential energy is rho g y because y is vertical and pointing upwards. Okay. So we are using y prime here. Okay. Which is the same as y. So PV, the pressure at point B, plus the density of the liquid times the acceleration due to gravity times the value of the y prime coordinate at this point, yb prime, plus half the density again of the water multiplied by square of the relative velocity at point B, which I'm calling W subscript B square. This will be equal to the pressure at point A plus rho g y prime A, the potential energy at point A, plus the kinetic energy, which is half rho WA whole square. Okay. Now PV and PA are the same as atmospheric pressure. So this term, the first term on the left hand side and the first term on the right hand side will cancel out. And W at point A here, we expect to be the water jet absolute velocity Vj minus the speed of the moving bucket. So that's the relative velocity. So this point A is close to the nozzle. Okay. And the velocity at A and C will be the same. You expect a uniform profile at this section AB. Okay. So absolute velocity at the section AC or CA is Vj, and the relative velocity is Vj minus U. So we know what is the velocity, relative velocity at point A. Can we find the relative velocity at point B? Well, if I look at this equation, there were three terms on the left hand side and three terms on the right hand side, but the first term here on the left hand side cancels with the first term on the right hand side because there is no change in pressure as the particle goes from point A to point B. But its elevation is changing. Okay. Now, we know what is VA. We want to find WB. Okay. So keep this term on one side and move this term to the other side. You will have a relation that WB whole square is equal to WA whole square plus 2G times this difference in the vertical heights, YA prime minus YB prime. Since the pressure is cancelled out, the density will drop out from the other two terms. Okay. And you have this half here, so we can multiply by 2. So the square of the relative velocity at this point B, the downstream point on the streamline, is equal to the square of the velocity at the upstream point A plus 2g times, you can call it h or whatever it is, which is the difference in the heights between A and B. Now I can factor out WA square here and write it as WA square plus into 1 plus this quantity 2g times h by WA whole square. H is this difference YA minus YB. As you can see, YA is larger than YB. Now you tell me what are the units of this term? Two G times this difference in the elevation by WA square.
Meter square per second square.
What are the units?
Meter square per second square.
Meter square per second.
G is meter per second square.
Yeah, and that is meters.
Meters, so the numerator is meter per second whole square.
Yes, sir.
This is meter per second whole square. So this is dimensionless.
Yeah.
Okay, it must be the case because left hand side is WB square and right hand side is WA square. So this entire quantity in parentheses has to be dimensionless. Okay, so if I take the square root, then WB is WA, which is Vj minus U, times square root of 1 plus 2 into G into this quantity to the power half. Okay. Now, do we expect this number to be large or small, this quantity?
Small, because YA prime minus YB prime is small.
Yes, this will be pretty small. Let us take an example. Suppose I say the jet velocity is say 150 meter per second. Okay. And U is say 50 meter per second. Then this difference will be 100 meter per second. So we have 100 whole square here. Okay, so 10 to the power 4. And G, let us say, is 10 meter per second square. It is 9.8, but let us take a round number 10. And if I say this is 0.1 meter, okay, then this is about 1. So this is a number which is very small. Now, even if this Vj minus U is 50 meter per second, then also it will be a small quantity. So if I do a binomial expansion, this 1 plus the quantity which is small raised to the power half, I can write as 1 plus half times that quantity plus higher order terms. Okay. So half and 2 will cancel out and you will have 1 plus G into H by this quantity, Vj minus U whole square. Okay. And this also we can approximate as 1. When this quantity here, 2GH by Vj minus U whole square is much less than 1. Okay. So that is the case. Then you say that WB and WA are the same. So the magnitude of the relative velocity along this relative streamline remains unchanged. Now what is the physical reason? The fluid is inviscid and the sum of pressure, relative kinetic energy and potential energy is conserved. If you look at the changes in pressure between these 2 points plus the change in the relative kinetic energy plus the change in potential energy, that must add up to 0. But there is no change in pressure because both are on the free surface adjacent to the atmosphere. Okay, so since you have air on one side of the water jet surface of the water jet, the pressure is the same at point A and B. So the change in the kinetic energy is the negative of the change in the potential energy. And the change in potential energy is small over here. So the change in kinetic energy is small. So if the kinetic energy is the same, that means the relative velocity magnitude at point A and point B will be the same. That's a very good approximation. Okay. So what we are saying that when the change in potential energy is small, WB is approximately WA, which is Vj minus Q. Now, a word of caution here. Whenever you say a dimensional quantity is small, you have to quantify how small is small. See, if the number is a non-dimensional number quantity, then you simply say it's much less than 1. Okay. Now, the same statement here I have written in a different way. I've taken this 2 in the numerator to half, moved it as half in the denominator and multiplied and divided by rho, so that you see that the numerator is the change in the potential energy of the fluid particle as it moves from A to B. Okay. This potential energy will decrease. And this quantity is the inlet relative kinetic energy. Okay. So this quantity much less than 1 means rho g times this quantity is much less than this quantity. Okay. So you can say that when the change in the gravitational potential energy is small compared to the inlet relative kinetic energy, then you can make this approximation. Okay. So this is an important concept, because if you look at a dimensional quantity, the number which quantifies its magnitude will depend on the units that you use to measure that quantity. So when you compare two dimensional quantities, when you say a dimensional quantity is small, you must say compare it with another dimensional quantity. Okay. So here physically you can say the change in the potential energy or gravitational potential energy of the fluid particle as it moves from one to point A to point B is small compared to what? Compared to the inlet kinetic energy at the section CA. Okay. Because the height difference is small. Difference in elevation is small. Okay. In that case, you can say that WB is approximately WA, which is Vj minus Q. Okay. So you have seen the application of what we are doing now. We are able to find the magnitude of the relative velocity on the free surface. Okay. Now if you make an assumption that across this outlet section the velocity profile is uniform, then you can say approximately the velocity magnitude, relative velocity magnitude at each and every point on the outlet section is going to be Vj minus Q. Now similarly, you can do a similar analysis and apply Bernoulli's equation in the translating plane between point C and point D. Okay. And what will be the conclusion?
Velocity at point C is equal to approximately equal to velocity at point D. Magnitude.
Yeah. Which velocity? The magnitude of the relative velocity.
Yeah, relative velocity, yes.
Okay. But the absolute velocity will actually decrease. Unless, of course, u is 0. Okay. If u is 0, the vane is not moving, then the absolute velocity is remain unchanged. And you're not extracting any energy from the fluid. Okay. Now, any other queries regarding this part? So what we have done is, the important concept that I'm trying to emphasize is that the flow is unsteady in one frame. The same flow can be steady in another reference frame. So relative to observer A, streamline pattern is unsteady, and hence the flow is unsteady. Relative to observer B, sitting on this moving frame, the streamline pattern is steady and the flow is steady. And therefore, if you take the velocities as measured by observer B, which is the W velocity, then you can apply Bernoulli's equation in the translating frame. This is the physical concept that you must understand. Okay. And I've given you an outline of the mathematics, why this should be the case. All right. So if there are no queries, then I'll close this document and open another document.
Excuse me, sir.
Yeah.
Could you press mute all once? Somebody's mic is, I think, unintentionally on. Thank you.
Pardon?
Thank you, sir. Nothing.
Okay. Now let us look at Reynolds transport theorem and its application to translating control volumes. Okay. So this is something you must have studied in your second year course. It is one of the first things that you study in a course on fluid mechanics. So you can view it as an extension of Leibniz rule for differentiation under the integral sign to multi-dimensions. So first let us review Leibniz rule. So suppose I have a function of x and t, one space dimension and time, let us say. And you're looking at this integral with respect to x from a time dependent lower limit at to another time dependent lower limit bt. Now the function that you're integrating is a function of two variables x and t. But after you integrate and plug in the limits, the x dependence disappears and it becomes a function only of time. So I've written as I of t, the integral. So suppose you have a function of this form defined in the time interval t between t1 and t2. So let us look at where the time dependence is appearing. There is time dependence in the lower limit, there is time dependence in the upper limit, and there is time dependence in the function also that you are integrating. So this is something you must have studied in your first year course on calculus. If f of xt and this partial derivative del f del t, which is another function of x and t, are continuous in both the variables x and t in some region of the xt plane, including this x lying between at to bt and time t lying between t1 and t2. And if at and bt are continuous functions and their derivatives are also continuous in this time interval, then d dt of this integral has terms. One term involves the partial derivative del f del t, integrated from the same over the same interval in x. And then you have the derivative of the upper limit multiplied by the function value at that point, x equal to b, minus the derivative of the lower limit here, this function, multiplied by the function that you're integrating with x equal to a. Now this assumptions are important, that f and del f del t are continuous and at and bt are continuous. But in most cases, those are satisfied, so you don't have to worry about it. Okay. Now, the extension of this to multi-dimensions is of this form, that if you have a function of x, y, z, t, which I'm writing for brevity as f of this vector r comma t, and I have a volume integral over a region which I'm calling r of t. So the limits of integrations are functions of time. And the function that you're integrating also depends on time as well as space. Okay. then the integral, you have integral of del f del t over the same region, plus you have this flux term, integral of f into Vs dot n dA over the surface which I'm calling del r. So this is does not mean a small surface. Del r is a symbol which connects the surface to the region which is enclosed by the surface. So of course this extended Leibniz rule is for the case where you have a surface del r enclosing a region r in three-dimensional space, and Vs is the velocity of a point on the moving surface, and n is the unit outward normal at a point on the same point. Okay. So if you compare this first term with Leibniz rule, it is analogous to this. Okay, and these two will correspond to this quantity over here. So if you have a one-dimensional case with one inlet and one outlet, then if you look at the second term here, the surface integral, you will have, when you account for the signs of Vs dot n, a plus sign here and a minus sign here, and this might represent the velocity at inlet and outlet, and this might represent the velocity of the surface at inlet, and these are the function values. Now this can be used, this is widely used in fluid dynamics to get a relation between the rate of change of an extensive property of a system and the rate of change of the same property for what you may call control volume. So we consider a control volume which coincides with the system which is moving at time t. So first of all, let us review what is an extensive property. So you know from your course on thermodynamics that an extensive property is a property which depends on the size or extent of the system. So examples are volume, surface area, mass, internal energy, enthalpy. So these are scalar properties. Then you might have linear momentum, which I'm calling this vector L in boldface, and angular momentum about some point, or momentum, which I'm denoting by this vector capital H. So do not confuse this capital H vector with this scalar H in italics. So I've tried to use symbols that you might see in your books, in the books that you've read on engineering mechanics. Now, intensive properties are properties that are independent of the size of, there's a typo here, size of the system. Okay. Examples are temperature and pressure. So these are intensive properties which an engineer can measure rather easily. Now you also have what you may call specific properties, which are also intensive properties. So any extensive property, if you look at the extensive property per unit mass, it's an intensive property which you may call specific property. The first example that comes to mind is specific volume, which is volume by mass. Now mass per unit volume is the density rho, so specific volume is 1 upon the density. Now if you look at a book on thermodynamics, they'll be dealing with, authors of thermodynamics text will be dealing with many thermodynamic relations. You see that all those relations are, if none of those relations involve explicitly this density, it will be in terms of the specific volume. But if you look at a book on fluid mechanics, they prefer to use, the authors of fluid mechanics text will prefer to use rho. But rho times V is 1. Okay. So if rho, the SI units of rho are kg per meter cube, so this will be meter cube per kg. So it's volume per unit kg or volume per unit mass. Similarly, corresponding to this internal energy which I've, so usually the notation is the extensive properties are denoted by uppercase letters or capital letters, and the corresponding specific properties are denoted by lowercase letters or small letters. So small e will be internal energy per unit mass or specific internal energy. So this SI units of capital E is joules. This will be joules per kg. Of course, quite often in thermodynamics text, it will be expressed in kilojoule per kg, otherwise the number will be very large. Okay. But when you solve problems, you have to convert it to joule per kg, otherwise the numerical answer may not be correct. Okay, you have to make sure that the units of each term in the equation is the same. Similarly, corresponding to this term, thermodynamic quantity enthalpy, which is H, which is internal energy plus P times V, you have small h specific enthalpy in joule per kg, which is small e plus PV. Now, once again, if you look at a book on thermodynamics, they'll use capital U for internal energy and small u for specific internal energy. But most books on fluid mechanics will use the symbol U for the x component of velocity. So to avoid confusion, I'm using small e instead of small u for specific internal energy. So this notation I've already introduced to you before. Okay. But this is just to give you an idea of what is a specific property. So specific property is an intensive property, and it can vary from point to point in a flow field. Now, what we are calling system is referred to as a closed system in textbooks on thermodynamics. So for a closed system, there is no mass transfer across the boundaries. Now, fluid mechanics, authors of fluid mechanics text also use this term material region, okay, for system. And I'm using the symbol R with a subscript M for material. And I'm using in writing in parenthesis T to denote that this region R is a moving region. Now, what is a system? Well, why is there no mass transfer across any part of the system boundary? The reason is that the velocity at any point on the surface, surface will be moving, but the velocity at the surface is equal to the fluid velocity. So if I say V subscript S is the velocity of a point on the moving surface which encloses the material region, that will be equal to the fluid velocity. So in that case, Vs dot n, the normal component of Vs, will be the same as V dot n, the normal component of the fluid velocity. Or if I define a relative velocity W, which is the absolute fluid velocity minus the velocity of a point on the surface, then W dot n, which is V minus Vs dot n, this will be 0. When this is true, then there is no mass transfer across any point on the boundary, any small area on the boundary. So the points on this material, so we can introduce another term which is called material surface, which is the surface of a material region, and I'll denote it by del Rm. Okay, now a material surface will always consist of the same fluid particles. The surface can stretch, but it will enclose the same matter at all instants of time, and the velocity at a point on the material surface is equal to the fluid velocity, and hence there is no mass transfer across any portion of the material surface. So a point on the material surface will move with the fluid velocity. Okay, so that means if a fluid particle is on the surface, the particle will move and the surface will move along with it, so that the particle always stays on the surface. Hence, what will happen is there is no mass transfer, and the material region will always consist of the same fluid particle. So if you look at the inside of the region enclosed by a material surface, you will always have the same particles, and hence the mass of fluid inside RMT is constant, and that is independent of time. Not only that, the identity of the matter inside is the same. at all instants of time. You can have an open system or control volume where the mass of fluid inside is constant at steady state, but mass might be entering and mass might be leaving, so that the identity of matter changes. But in the case of what you are calling a system, the identity of the matter is the same. So it is like a body to which you can apply, say, Newton's laws of motion. Okay. Now this system will translate, rotate, and deform continuously. So you have studied rigid body dynamics. You know the most general motion of a rigid body is translation plus rotation about its center of mass. Okay. But in the case of a fluid, the most general motion is translation plus rotation plus deformation. And some of you may be taking the course on advanced fluid mechanics. So you will come across a term which is called the Cauchy-Stokes decomposition theorem. So the Cauchy-Stokes decomposition theorem tells you that the most general motion of a fluid is translation plus rotation plus deformation. An elastic solid will deform, but not continuously. There is a finite deformation, and after deforming it will stop. But a fluid may deform continuously, and that forms part of the motion. Now, the volume of this volume enclosed by the material region could change with time if the flow is compressible, that is, the density can vary. But if the flow is incompressible, okay, then the volume is conserved, but the shape may change. So in addition to translating and rotating, it might deform. But it might, if the flow is incompressible, the deformation will preserve the volume. The fluid particle which is on the surface will always remain on the surface, and the fluid particle which is inside will always remain in the inside. So these are the characteristics of a material region or system. Now suppose I say capital phi is an extensive property and small phi is the corresponding specific property. Consider a region of infinitesimally small volume, say dV, surrounding a point P, and let rho be the fluid density at point P. Then the particle which is at point P inside this volume dV will have mass dm, which will be the density times dV. So units of density is kg per meter cubed. You multiply it by meter cubed, we get the mass in kg. And associated with this mass, there will be a extensive property which I am calling d of capital phi, which will be, so d of capital phi, which is the property of the fluid inside the region of volume dV, it will be the specific property phi multiplied by the mass dm, or phi times rho dV. So if you want the property of a system, then you have to integrate over the entire volume occupied by the region. So it's a volume integral over RMT of rho phi dV. And here I have indicated the, in general, density could vary with position and time. For us, of course, it will be a constant because it's a liquid, but phi can vary with position and time. So the function that you're integrating, rho phi, the product, will depend on the spatial coordinates as well as time. But after you integrate and plug in the limits, the spatial dependence disappears, and it is just a function of time, which I'm calling phi with the subscript s phi s for the system. Similarly, if you have fluid inside a control volume, the property of the fluid which is inside the control volume at time t will be given by a similar integral, but the region of integration will be what I'm calling R with the subscript Cv. And if the control volume is moving, then that can be denoted by this parametric dependence RCV of t. If the control volume is stationary, then it will, the limits of integration will be constant. But if you want to apply a Reynolds transfer theorem to a Pelton turbine, then we have to consider a translating control volume. So RCV, then this region, the limits of integration which define this region, there will be functions of time. So Reynolds transfer theorem for stationary control volumes is something you must have seen in your second year. So what we do is we take a control volume which coincides with the system or material region at time t. So I've denoted it by R with the subscript COIN for coincident, and del R with the subscript COIN for the surface of the coincident control volume. All right. Now, if the first I gave you the result, the extended Leibniz theorem for an arbitrary region here, R, just call it R of t, and I've called it Vs of, which is a velocity at a point on the surface. The proof of this you can do using a geometric approach similar to what you see in any standard book on fluid mechanics. But fluid mechanics textbooks don't give you in this general form. They give it to you for the case when there is a material region. Now, what is the difference? Well, if it's a material region, Vs will be equal to V. So Vs will be equal to V, the fluid velocity, if this region R is Rm. Okay, so here I brought the subscript S. Okay.
Sir, pardon.
Yeah.
Sir, that the other part, that V dot n part, that is relative velocity, or that is the I mean that V is in which reference frame? That dot V dot n dA.
Yeah. V is a vector and n is the unit outward normal.
Yes, in the surface, but that V is the relative velocity. That I'm asking, that V is in which reference frame?
Instead of Vs, so instead of R, I have Rm here. Okay. So when it's Rm, the Vs must be V. Okay. And here I'm taking a coincident control volume. So this second term physical interpretation is the flux of the property through an open system which coincides with this closed system at time t. And this is the rate of change of the property of the fluid which is inside the open system. Okay. So left hand side, the RMT is for the closed system or material region, which is simply called system in fluid mechanics. And this coincident control volume, see, control volume is a term which is used by authors of fluid mechanics texts. Authors of thermodynamics texts will use the term open system. So the Reynolds transport theorem actually will give you a link between the rate of change of an extensive property for an open system and closed system, but not any arbitrary open system and closed system. You have to take an open system which coincides with the closed system at time t. At a later instant of time, if the control volume is stationary, the system might have moved and it will not occupy the system at time t, other instance of time. Only at time t, the region occupied by Rm and the region occupied by the control volume are the same. Now, you can generalize this to a case where the control volume is translating, and all you have to do is replace this R coincident by RCV of t. Okay, so I'll do this again next time, but today let me give you the result. So as an example, I have considered this control volume shown by dotted lines, which is attached to the moving vane. So this is a translating control volume where section 1 is the inlet, section 2 is the outlet, section 3 is the outlet, and section 4 is the other side of the vane which is exposed to the atmosphere. Now you have ddt of phi system is ddt of integral over rmt of rho phi dv, which will be this arsthetic term plus this flux term. So the form is similar to what I've already shown you. Only thing I've just written RCVT here and del RCVT. So there are three things now. You can have a system at time t. Consider the position of a system at time t the control volume at time t, and a coincident control volume at time t. So all three coincide at time t. At a later instant of time, the system moves in a certain direction and the control volume may move in another direction. And the coincident control volume may remain fixed. Okay. But this relation is still valid. However, when the control volume is moving, this unsteady term may be non-zero and it may be a large number. Okay. So here V is the absolute velocity of the fluid particle. And this is the temporal derivative in the stationary frame. So this is not very useful when the flow is unsteady in the stationary frame. An equivalent form, which I'm calling form 2, is you have del del t prime. So I've gone to great lengths to explain what is the difference between del del t and del del t prime. So this is the temporal derivative in the translating frame. Okay. And here you have the relative velocity, W. So if you have the absolute velocity here, then this is the del del t in the stationary frame. And it is equivalent to this equation where you are using the relative velocity here and del del t prime over here. So this is the flux evaluated using the relative velocities. And relative velocity is V minus, so here Vs is U. Now, Vs can vary from point to point, in which case the control volume can deform. But if you say the control volume is translating, its shape is unchanged. And the velocity at each point on the surface is simply the constant velocity capital U. Okay. Now, why is this form useful? Because in many cases, the flow may be stationary, steady in the translating frame, in which case the first term will be 0. And all you have to do is find the flux of the property using the relative velocity. Okay. So I'll go through this again in the next class and see how we can apply this to the Pelton turbine, and we'll be using this form. So form 2 and form 1, they are equivalent. Okay. All right. For the timing, any questions? If there are no questions, then we can